Chapter 2. Okay, now we on 2.4, wireless LAN transmission techniques. Okay, so on this part, okay, so wireless LAN technologies use transmission technique that can be broadly classified as radio frequency and infrared on the RF ataupun IR, infrared. Okay, RF technology can be narrowband or spread spectrum. Okay, narrowband technology include microwave transmission. Microwave technology can be used to connect two LANs located in separate building. Wireless LAN transmission teknik bagi pada dua kan. Okay, so untuk nak connect dua ni kita pakai microwave. Nampak tak? Okay, kalau tak nak wire lah. Kalau tarik wire apa salahnya kan? Tapi kalau jauh tak tarik wire panjang ni. Contoh kat sini 40 km kan. 2 km. So, dia boleh pakai microwave dengan microwave. Okay, narrowband versus spread spectrum. So kita tengok different between narrowband dengan spread spectrum. Okay, untuk narrowband, so use only enough frequency to carry data and no more. But on spread spectrum, information can be sent using narrowband carrier signals spread out over a much larger frequency range. Nampak sini? So kat sini kita ada 3 band radio bands for transmission under 1 watt of power. 1 watt power saja, tapi boleh ada 3 radio bands. Okay. Contoh ni 900 to until 9 to 8. Okay. 2400 to 2483.5 and then 5752.5 dengan 5850. Okay. Second, untuk narrowband high peak power. Okay, more power required to use a smaller frequency range. Nampak tak? Power dia high peak. Okay, but on spread spectrum, probably a signal corruption or jamming is greatly reduced. Signal must be stand out above inherent RF noise level or noise floor in order to be received. Kan on narrowband. Tapi untuk spread spectrum, peak power is very low. Kan? Tadi kan sebut jam tadi kan? Untuk narrowband can be jammed easily. Alright. Lain can experience interference easily. Kan? Selain daripada jam juga interference easily. Alright. Untuk spread spectrum, signal looks like noise to most receivers. Next. The most widely used transmission technique for wireless LAN, the term spread spectrum refers to transmission channels spread across the spectrum of the available bandwidth. This is done by spreading the signal over a range of frequency. The bandwidth of the transmitted signal is much greater than the bandwidth of the original message. The bandwidth of the transmitted signal is determined by the message to be transmitted and by an additional signal known as the spreading code. Initially developed by the military to avoid jamming and eavesdropping of the signal. Keluar ni kejap. Keluarkan dia kejap. Macam itulah bila recording kan. Okay, two types of spectrum communication. One is FHSS. Apa tu? Frequency hopping spread spectrum. Ataupun yang second adalah DSSS, direct sequence spread spectrum. So kita daripada RF tadi, kita ada dua narrowband dengan spread spectrum. Di atas tadi dah ada dua, RF dengan IR. RF ada narrowband, ada spread spectrum. Spread spectrum ada dua pula, FHSS dengan DSSS. Okay, FHSS dulu. This technique broadcasts the signal over a seemingly random series of radio frequency. In FHSS system, the spreading code is the list of frequencies to be used for the carrier signal, aka the hopping sequence. A receiver hopping between frequencies in synchronization with the transmitter receive the message. The message can only be fully received if the series of frequency is known. So because only the intended receiver knows the transmitter hopping sequence only that receiver can successfully receive all of the data. Most vendors develop their own hopping sequence algorithm in order to guarantee that two transmitters will not hop to the same frequency at the same time. Implement in Bluetooth and walkie-talkie, unlicensed 900 MHz or extreme radio service. So primarily apply in low data rate wireless applications such as utility metering, machine and equipment monitoring and metering and remote control. Okay. So kalau kita tengok time frequency equation for FHSS, time ni yang kat garisan bawah. Right. So kalau ini panggil dual time. Dual time. Okay. Yang bawah ni panggil FH code period. F ni frekuensi ya. So ada banyak frekuensi. Sini contoh ada 9 frekuensi. So dia tak tembung lah. Kan? Dia tak tembung. Over a time. Okay. Time first time. Siapa jalan dulu? Frekuensi 0. Second time. Time yang second. Frekuensi 2. Time yang next adalah F7. So nampak dia punya macam mana komunikasi berlaku. One period, one frekuensi. Alright, so this is yang kalau ada satu time ada dua signal, dua frekuensi pakai, kita panggil the coexistence of different FHSS signal. Biru dengan merah serentak pada time yang sama. Signal 1 dengan signal 2. Alright, merah tu signal 1, tiba-tiba ada signal 2 kan. Boleh. Alright. Okay, this is frequency hopping system block diagram. Okay. So, ni sebelah transmitter. Sender lah. Sender nak hantar dekat receiver kan. From the receive, apa dia buat? Kita punya data kita dalam digital, kita akan tukarkan dia pakai modulator FSK atau BPSK. Okay. So, dia akan sampai dekat FH spreader untuk nak spread. Okay. So, kat sini dia ada coding lah. Pseudocode untuk pseudo noise bit source. Dan check dengan channel table, ada frequency synthesizer. So, bila dia guna macam coding, kan, masuk dalam kita punya apa nama program, kan, coding dalam bentuk program kan. So, dia akan keluarkan program ni, kan, program. Dia akan keluar sebagai spectrum signal ataupun main pass filter about some frequency. Okay, so kita nak dapat balik sana, kita kena tukarkan balik guna coding yang tadi dan check dekat channel table nama dia frekuensi synthesizer. Okay, on this part kita panggil FH this spreader. Tadi spreader kan, ni this spreader. Kita daripada spread kepada this spread. Right, so dia akan keluar filter dulu balik, and then lepas tu baru kena demodulate. Dapatkan balik data kita. Ini sebelah receiver. Okay, for HSS. Okay, untuk DSSS, this method seems to be the one that most wireless spectrum lens use. Yang ni kita pakai dekat wireless. Direct sequence transmitter spread their transmission by adding redundant data bits called chips. In the DSSS system, the spreading code is the chip sequence used by represent message bit. Like frequency hopping receiver, a direct sequence receiver must know a transmitter spreading code to decipher data. The spreading code allow multiple direct sequence transmitter to operate in the same area without interference. Once the receiver has all of the data signal, it uses a correlator to remove the chips and collapse the signal to its original length. Okay, kalau tengok sini nampak sikit je kan, tak macam tadi kan. So sebelah transmitter ni ada modulator juga. Okay, so masuk kita punya pseudo-noise bit source ni, coding kita. So dia akan keluar sebagai spektrum dan dia masuk balik dekat DS spreader. Dia sama juga. Tadi ada FS spreader, ni ada DS spreader dengan DS spreader. Right, so spektrum signal masuk balik pada receiver, sebelah receiver, dan dia akan demodulate untuk dapatkan binary data. Hari ni kita buat dekat chapter tutorial chapter 2. Okay. Sabar, tunggu hari apa lah. Tak present. Tengok kamu punya result kan untuk tutorial tu. Alright. So, transmitter dengan receiver. This is example. So contoh di sini transmitted signal pakai XOR kan, exclusive OR. Okay. Data input macam ni, locally bit stream macam ni, and then transmit signal dia akan dapat last yang ketiga ni, line ketiga. Okay, so dia dapat line yang ketiga ni, dapat pula dekat receiver, dia masuk balik dalam bit ni, and then dia akan diikutkan terjadi balik daripada apa nama data yang asal. So macam ni 0, 1, 0, 0, 1, 0, 1, 1. Senang je. Alright, so boleh tengok dekat YouTube ni. YouTube pula lah. Tak ada link pun. Tak ada link. Untuk insert media video online. Control V. Ya. Ada. Okay. Okay. Lagi. Ada suara tak? Suara. Sekali lagi. Ulang suara. Stop sharing. Sharing. Put sound. Screen.
Good morning. This is a video where a user has some data and he wants to spread it using a Walsh code. Are you ready? So what we have user number 1. And good morning. This is a video where a user has some data and he wants to spread it using a Walsh code. Are you ready? So what we have user number 1. And user number 1 has some data. So those are 2 bits that the user wants to send. And the user is also going to spread the signal. And the user is going to spread that signal with a Walsh code, and that's the Walsh code they're going to use. So you start with the code, and you apply the code to the first bit. So the first bit is this one. So you put data here. So data, the first bit is a 0, so you just repeat it like that. Then you apply the code again to the next bit, like that. And then you use the exclusive OR. And what is the exclusive OR? It's when they're the same, you get 0, and when they're different, you get 1. So these are the same, you get 0, different, you get 1, 0, 1, and same is 0, different is 1, like that. So then you can say that user number 1 has a spread message that looks like this. So the data itself is 2 bits, and the spread message is 1, 2, 3, 4, 5, 6, 7, 8 chips. Good morning. So we've already spread user 1's data, and now we're going to do the same with user number 2. So we have user number 2. And user number 2 has some data. The data, 2 bits, 1 and 0. And user number 2 has a spreading code as well. So we're going to spread user number 2's data the same way we did with user number 1, except the data is different and the code is different. So, spread the signal. We'll start with the code and the data. So the code is 0, 0, 1, 1, and the first bit is 1. So we put the data like that. The first bit is 1. And then we do the code again, same code. Second bit is 0. And then we again do the XOR. Different is 1, same is 0. So different is 1, 1. These are the same, same is 0. Different is 1. So then we have user number 2 spread message, which works out to be 1, 1, 0, 0, 0, 0, 1, 1. And just like the first time, we started out with 2 bits, and we end up with 1, 2, 3, 4, 5, 6, 7, 8 chips. Good morning. So now we have we've already spread user 1's data and user 2's data. We're going to do that with number 3. So we have user number 3. The data is 1, 1. And user number 3 also has spreading code, which is different from the rest of them. Each user has a unique code, and each user has its own data. Then we will spread the signal. The code and the data, just like before. So the code here is we go. The data is, the first bit goes here, the second bit goes here, XOR, and we know that if it's different, it's 1. If it's the same as 0 in all of these cases. We end up with that. So then we have user number 3 spread message looks like this. So just like before, we started with 2 bits, and now we have 8 chips. Okay, so we have 3 users, and each user has its own data, and each user signal has been spread with a unique code. So now we want to combine all 3 signals. And the way that we're going to do that is we're going to create waveforms. So how we're going to do that? Well, I've decided that I want to represent a 0 bit as plus 1 volts, and I want to represent a 1 bit as minus 1 volts. So that's what I've decided to do. So watch this. So I've got here user 1, and that's the spread signal, 8 chips. User 2, spread signal 8 chips. User 3, spread signal 8 chips. So this is what we came up with in the last few videos when we took the data and spread it. So now, waveform, I'm going to say this is plus 1 volt, this is minus 1. And what did I say? I said a 0 is plus 1. So I'm going to go like this. That's 0, that's a 1, that's a 0, that's a 1, that's a 0, 1, 0, 1. That's user 1. User 2, if that's plus 1 and that's minus 1, then a 1, that's minus 1, so we'll like that. Like that. And user 3, well, this one will be easy, plus 1 and minus 1. So 1 bit is minus 1 volts, so I have 3 unique waveforms which represents the spread signal. That's what we've got so far. Okay, so we have user 1, user 2, user 3. We've created waveforms which represents each user. But if we had all of these users using the same frequency at the same time, then the resulting signal would actually be this signal added to this signal added to this signal. So that's what we'll do. So what do we got here? We've got plus 1, minus 1, and minus 1. What's 1 minus 1 minus 1? That'd be minus 1, I think. Okay, so then we have a minus 1 and a minus 1 and a minus 1. That sounds like minus 3 to me. Plus 1, that's 2. 2 minus 1 is 1. And minus 1, plus 1, minus 1 works out to minus 1. So this one is plus 1, minus 1. That's 1. And then we have minus 1, plus 1, minus 1. Turns out to minus 1, plus 1, minus 1, minus 1. And minus 1, minus 1, minus 1. That works out to minus 3. So if we wanted to create a composite waveform, so this would be the waveform that every single user receives. So if we have, let's say, 3 volts, 2 volts, 1, 0, minus 1. So this is just so 0 would be here. I'm going to represent this minus 1. Here's minus 1. And then minus 3. I know you can't see that. There. And this is up to 1. Down to minus 1. Back up to 1. Minus 1. Minus 1. And minus 3. So this here is if we took each individual user's signal, converted it to a waveform, added them all together, so every user's signal is here. So every receiver is going to receive every receiver is going to receive the composite signal. Okay, this is the best part. Are you ready? So this is user 1. User 1 is we have the data and the spreading code, and the signal has been spread and then combined with the signal from 2 other users. So we have a composite waveform which contains 3 users worth of data. Contains 3 users data. So what we're going to do is we're going to take the user 1 code, and what is that code? Let's look it up. We use the code 0101. So if we convert that to a waveform, the 0 bit was represented as plus 1 volts, and the 1 bit was represented as minus 1. So this would be plus 1 volts. And these ones are minus 1 volt. So 0, 1, 0, 1 would look like plus 1, minus 1, like that. 0, 1, 0, 1. And we apply the code again. 0, 1, 0, 1. So this is the magical part. Then we multiply them. So we have minus 1 times plus 1. We end up with minus 1. We have minus 3 times minus 1. We end up with plus 3. We have 1 times 1, 1. Then we have minus 1 times minus 1 is 1. So then we go, what does that work out to be? Minus 1 plus 3 plus 1 plus 1 equals 4. But this is occurring 1, 2, 3, 4 times, so we average that out. It works out to be 1. Okay, so now we'll just try this one. Plus 1 times plus 1, 1. Minus 1 times minus 1, 1. Minus 1 times plus 1, minus 1. Minus 3 times minus 1 is 3. So what do we got here? We've got 1 plus 1 is 2, minus 1 is 1, plus 3 is 4. That's 4, but then 4 is occurring across, so we're dividing it by 4 equals 1. So we have a plus 1 and a plus 1, but this is really 1 volt. Plus 1 volt represents a 0 bit, and plus 1 represents a 0 bit, which, if I show you the original thing that we looked at, remember this? User 1's original data, 0 and 0. So you see what happened was, user 1 spread the signal with a spreading code, user 2 did the same, user 3 did the same, all those 3 signals were added together, then we applied user 1's code to that composite signal, and magically, the original data was recovered, 0 and 0. So now you can try it for user 2 and 3, and hopefully you'll find that the same thing happens.
Okay, so tadi dia cerita nak hantar 2 je kan, 2 bit saja, nampak tak? Over signal spread, spread kan? Dia nak spread 3 user kan. So dia akan dapat signal lain-lain dan dia guna calculation ataupun program untuk nak kira balik dia punya nombor tu supaya sebelah di spread nanti boleh dapat balik nombor kan. Yang user 2 dengan 3 tu dia suruh you all kira lah macam mana dapat balik dekat di spread dia. Okay, panjang cerita lah. Ni yang baru tunjuk 2 bit saja kan. Boleh continue ke ni? Ya. Okay, difference between FHSS and DSSS. Okay. Okay. Kita tengok different based on power consumption. Use less power, DSSS use more power. Cost less expensive, the FHSS less expensive than DSSS. Kita rate menangkan DSSS lah. Okay. 11 to 33 megabit per second, but FHSS around 2 to 3 megabit per second. If high performance is key and interference is not a problem, go with direct sequencing. But if a small is inexpensive portable wireless adapter for notebook or PDA is needed, the frequency hopping method should be good enough. with either method or spectrum, and the end result is a system that is extremely difficult to detect, does not interfere with other services, and still carries a large bandwidth of data. Okay, so different spectrum dengan infrared, kan? Infrared kan yang tadi type yang kedua kan. Okay, frekuensi dia infrared tinggi lagi kan. 10 the power of 14 Hz kan. 14 apa? Cepat. Kalau 12 apa 12? 12 GHz lah. Billion GHz. Macam ni 30 20 okey 20 12 20 300 GHz ni. Betul? 6 mana tera dah ni. Terahertz lah. Macam mana nak conteng? Macam mana nak conteng? Macam conteng? Okay. Kita ambil dah lah. Saya tahu lah. Only you can edit. 14 ni kita ambil yang 12. Kali 12 so tinggal lagi 2 kan. So jadi 3 kali 10 kuasa 2 300 lah. Betul? So bila 12 ada 12 power 9 kan. Satu. So ini kilo, mega, giga, tera. Betul tera. 300 terahertz. Kan? Okay. So coverage spectrum pergi jauh kan. Infrared masalah dia coverage dia tak jauh lah, tak boleh jauh. Line outside required no, tak perlu, and then infrared kena ada line outside. Okay, transmit power kurang pada 1 watt, WATT kan. Okay, infrared tak ada. License required, dua-dua tak payah. And then data rate infrared lagi tinggi. Ke tengah-tengah. Oh, bukan. Data rate ni lagi tinggi. Spectrum. Kan, DSSS kan. DSSS. Ni yang kecil FHSS. Clear? Alright. Itu kena nak tutup. Saya dah tutup. Kita nak keluar balik. Tak payah. Next. Okay. So untuk IEEE 2.11b DSSS channel allocation. So kamu tengok sini channel ada sampai 14 kan. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So kalau tengok channel mana yang tak bertembung. Channel 1 tak bertembung dengan channel 6 dan tak bertembung dengan channel 11. Can you see?